Today, I'm talking about surface analysis techniques in the ARC. The main instrument I'll be talking about today is the XPS, or X-ray photoelectron spectrometer, but we also have a stylus profilometer. Very broadly, surface analysis involves trying to understand the physical and chemical phenomena occurring between two phases. So this can be a very broad area for study. Oftentimes it has to do with trying to see whether some sort of surface treatment worked, if something is there or not, how something might be corroding. It might be really important for catalysis, where interactions on the surface of material are vital to understand. We have some groups at CSU who do biomedical engineering, and so they're often looking to see whether some treatment that they've done worked, or whether their surfaces are compatible in various situations. And then we have some groups studying photovoltaics and semiconductor devices, and they're really interested in the composition of their thin film surfaces. Electrochemistry is a very broad term, but a lot of people doing battery work come through and are trying to see how the surface of their electrodes age as they cycle batteries, for example. So basically solid dry samples are what we look at, but this can vary in a number of different areas. I'm just going to talk about the profilometer first because it's very simple. Just kind of get it out of the way and then talk about XPS more. This is a close-up view of that stylus that we have. So we've got a diamond-tipped metal stylus that's dragged across the surface, and we measure the 2D profile. So we can set the distance, how far we want it to measure, time for sort of resolution, and then the force of that probe. Again, we need dry solid samples, and the features can't be so tall that they don't fit under the device here, kind of shown. About 2 millimeters would be maximum. In the end, you get, this profile. You can calculate surface roughness from that, and a bunch of other properties. Generally, this is kind of what some data might look like. We've got, the distance that we move the stylus along on the X, and then the profile on the Y, the Z height. So from this data, we might be able to calculate what the height of these features are, how wide they are. We could select just the top surface of them and have it calculate the surface roughness of that. And as you can see, the Y scale is in nanometers, whereas the X is microns. So you'll get much better Z height resolution than spatial because that stylus tip is like 12.5 microns across anyway. This shows a much finer featured 2D profile, so you can see just the Z height features that it's looking at are on the order of individual nanometers. I think, the brochure claims that you can kind of get at best about a nanometer resolution or so. It's definitely not as good as like a AFM instrument, but for being able to move around visually and choose a location on your sample, I believe it's easier to operate in that sense. And then here's an example of a 3D map where 2D line scans are stitched together. So this was taken on a penny, as you can kind of see, and these individual line scans in the sort of Y direction as shown here were all stitched together. And then these two white lines correlate with the data on the left side here. So for example, this top one here was one of the line scans measured sort of up and down the white line here. And then at that point for each of the line scans, the data points stitched together on this horizontal white line correspond to this. So you can kind of move this crosshair around to view each of these sort of X and Y components of the data set. Yeah, that's all I have really for the profilometer. I don't know if there are any questions on it before we move on to XPS. I'm also happy to take questions at the end. Right. So XPS, or X-ray photoelectron spectroscopy, is a very common surface technique. Our instrument that we have here at CSU is from Physical Electronics, or PHI, a 5800 multi-technique. It's a decently old instrument, does the basics well. Yeah, and the main information you can take away from XPS is listed here. So you're getting information from the top 5 to 10 nanometers or so of a material surface, and we can identify and figure out the rough concentration of elements at the surface. You should keep in mind, though, that detection limits vary based on what the element is and what it's in. For most elements, that detection limit's about 1 to a tenth of an atomic percent. But if you have a really light element in a heavy element matrix, then it's much harder to detect that element. So that could be up to as high as 10 atomic percent needed in the sample to even see it by XPS. And there's a really nice publication here linked below that calculates that for basically any element in another element, and shows you sort of these maps of what the detection limit would be. Then, if you scan at high resolution, high energy resolution, you can assess the chemical bonding state of those atoms on the surface. So, yeah, what their nearest neighbors are basically in terms of electron negativity. That's kind of a rough explanation. Then there are ways to assess how the composition of your surface changes with depth, either on a very shallow depth, sort of in those top 5 to 10 nanometers, or destructively assessing how things change as you ablate the surface and go deeper into the sample. But then you have to keep in mind how you might be changing your sample. And you might not be measuring exactly what it was like before you took layers away. And then in newer XPS instruments, there are capabilities for doing sort of spatial mapping of these chemical bonding states and composition. That's not something that we can do with our instrument, but I'll talk a little bit more about efforts to get a new XPS here at CSU and what that kind of instrument would be able to do compared to our current capabilities at the end. All right, so the main XPS process relies on the photoelectric effect. So we have monochromated X-rays focused onto the surface of our sample. These are from an aluminum K-alpha source. So the energy is listed here. Atoms within your sample have core electrons kicked out of them. And if one of those electrons escapes the surface of the sample and makes its way into the detector measures the kinetic energy of that electron. And then based on this equation, knowing the input X-ray energy, measuring the kinetic energy of that ejected electron, and knowing the work function of the spectrometer, we can calculate the binding energy of that electron, which you can kind of think of as how tightly that electron was held. And that's what's plotted in XPS data, the binding energy. So as kinetic energy, if kinetic energy is higher, then the binding energy is lower. This shows an example of a survey spectrum. So this is kind of the first data set that you would collect on a sample. It's a wide energy range. You'll notice for X, we have the binding energy from high to low. That's also because the kinetic energy goes from low to high of those emitted electrons, and then counts on the y-axis. The settings for taking survey spectra have low energy resolution, so there's big step sizes, but it's really sensitive, picks up a lot of signal. So we can collect a survey spectrum in about 10 minutes, see which elements show up on the surface of our sample. This is always a good idea for a number of reasons, but you never know what might be on the surface of your sample. Even if you have a good understanding of what your sample is made of, there might be some potential contamination. And it's good to check to make sure there isn't some other salt or some other component if you, let's say you have a salt on the surface of your sample, but you know you want to just analyze carbon and oxygen, those other elements might complicate the carbon and oxygen peaks. And if you just honed in on those initially as high resolution spectra, then you're left without some information about how to analyze the system or the sample. It's also a good idea to understand whether there might be peak overlap based on knowing which elements show up. It's good to check for secondary peaks to make sure, these Auger peaks for fluorine also show up, and it's not just something else that has a peak here that you're assigning to fluorine. Yeah. Okay. This shows sort of a screenshot of our handbook from Phi with reference spectra. So I just this previous one only showed elements that have 1s peaks. They're pretty clean. But for something like silver, for example, you get multiple peaks for one element within the survey. And let's say you have a combination of elements. You know that this 3D peak is your main silver peak that you're going to be analyzing at around 370. However, you want to make sure that other peaks from silver don't overlap with a main peak from another element of yours. So when you know which elements are in your sample, when you see what's in the survey, it's always a good idea to take a look at the reference spectra and make sure that you can anticipate whether there are going to be overlaps between elements for analysis. And this is a book that we have by the XPS, as well as a PDF form of it on Teams for our users. Okay, let's talk about signal depth. So the X-rays absorb relatively deeply into the sample on the order of microns, which means that electrons are being kicked out of atoms that far deep into the sample. So if an electron's kicked out sort of far into the sample, it's going to inelastically scatter at various points before it makes its way to the surface, if it does. And when it then gets ejected from the surface of the sample, it has a lot lower energy than it did when it was initially ejected. So these are called inelastically scattered photoelectrons. They might still escape and make their way to the detector. Electrons that are kicked out of atoms close enough to the surface of the sample where they don't scatter and lose energy and make their way to the detector are what contribute to these photoelectron peaks. So this peak is composed of electrons that were detected coming from fluorine 1s shells that hadn't lost energy from scattering and come from probably the top 5-ish nanometers of the surface of your sample. So if these inelastically scattered peaks lose some energy, that means they have a lower kinetic energy, which means a higher binding energy. And that's why in these survey spectra, you see this step around big photoelectron peaks. So the step in the background comes from fluorine atoms deeper down in the under the surface of your sample that have electrons kicked out, that have lost energy, but have still made their way to the detector. You can kind of qualitatively take away some information from this background in the survey. For example, carbon has this step, fluorine has this step, but oxygen really doesn't have much of a step at all. Granted, it is a much smaller peak, so it wouldn't have as big of a step, but that might be an indication that oxygen is just really only on the surface of your sample, not deeper down in your sample, whereas fluorine and carbon do. And then what's not labeled here, there's maybe a tiny peak around 400, and that could very likely be nitrogen. Yep. Okay. Another process that can happen when we have this core electron ejected from our atom is that an electron from an upper shell can drop down to fill that hole. And if this sounds familiar from SEM EDS, it's because the electron beam causes the same secondary electron ejection. And if an upper electron falls down, an X-ray can actually be given off. And that's what the EDS detector in SEM picks up to figure out which elements are where. But there's another process that can happen when this electron falls down, and that could be the ejection of another electron within that same atom. And that's called an Auger electron. So these might also escape the surface of the sample and make their way to the detector. They're picked up and their kinetic energy is measured. They're part of the spectrum. and X-rays being given off or Auger electrons being kicked out happens in both the SEM and the XPS. It's just a matter of what the instrument is set up to detect and take advantage of signal-wise. All right, so most XPS instruments have the same X-ray source that we do, a monochromated aluminum K-alpha source. However, it is possible to have a different X-ray source for an instrument or multiple ones on the same instrument. And for different X-ray sources, photoelectron peaks energies stay the same no matter for binding energy, stay the same no matter the input energy. But the Auger electron peaks shift in terms of binding energy if you have a different X-ray source. And the reason for that is because if you have higher input X-ray, then the kinetic energy of the ejected electron is also going to be higher proportionally. And so there's no change to the binding energy for that photoelectron. However, for this Auger transition, that's totally unrelated to the input energy. And so if you have a higher energy input X-ray, but the kinetic energy of the Auger electron is still the same, then you see that change in the binding energy, and that's what's plotted for XPS. So just keep that in mind if you're ever working with a different X-ray source. Also, it can be a strategy if you have an Auger peak that overlaps one of your photoelectron peaks. If you can use a different X-ray source, then you might be able to isolate that photoelectron peak you're interested in. All right. So now we talked about survey spectra. Next, what you might collect is what's called a high resolution spectrum or spectra of different energy regions. So we set specific energy regions to scan and use higher energy resolution settings for our analyzer that also limit the number of electrons that we can count. So we have to go to higher collection times. But we can actually see peaks. Yeah, we have better energy resolutions so for a survey, this would just look as one broad carbon peak. But in the high resolution spectrum, we can see there are multiple carbon binding environments for this molecule. You can see they're sort of equivalent fluorine atoms within it. There's just this one fluorine binding environment. We've got two different oxygen binding environments. You can kind of see this sort of plateau of a peak. So there's probably two equal components under this oxygen peak. And then what's really nice about this example is that these 4 carbon atoms basically directly correspond to these 4 peaks. Yeah, and I'll kind of talk about it a little bit more, but there's a reason why something like a carbon bound to 3 fluorines would be at the highest binding energy, whereas carbon with either carbon-carbon, carbon-hydrogen bonds is at this lowest binding energy. Yeah, here we go. So the binding energy, if you want sort of the strict definition, is the energy difference of the atom in the ground state versus that of a positive ion with a core hole state after photoionization. So the way that I think about it is what are the nearest neighbors of the atom and how electron negative are they? Because when you have carbon bond to 2 fluorines, for example, you get a lot of electron density pulled away from the carbon atom, slight positive charge around it, and when you're ejecting an electron from that electron is held tighter. So you see a higher binding energy in XPS. For metals, you kind of think about this in terms of the oxidation state of the metal, with maybe like metal-metal bonds at a lower energy, binding energy, and metal oxide bonds at a higher binding energy. We have these sort of reference tables that show general trends of where peaks might show up. This is, again, from now low to high, so kind of mentally switch that around when you're thinking about the plots. But yeah. And then so far, I've only shown you peaks that have 1s spectra. And those are just singular peaks for one binding environment. However, when you get to the p, d, and f orbitals, you get splitting of the peaks from spin-orbit coupling. So, for example, these 2p peaks for sulfur and zinc both show this larger 2p3 halves peak and a smaller 2p1 halves peak. For sulfur, the split of these two should always be 1.18 EV, or very close to that. So if you have multiple sulfur binding environments, you would see multiple paired peaks. And then because of the number of elements or electrons that contribute to these two peaks, 2p peaks will always have a 1:2 area ratio. It's true for all of the elements with p peaks. For d and f peaks, the ratios are different because there's different number of electrons, so 2:3, 3:4. And these are taken from that handbook from Phi. So you can look up where the main peak should be for elements, how far apart the splitting should be. And use these as controls when you're fitting your data. I wanted to show you kind of a more complex example where there are multiple binding environments for paired peaks. So these are 3D molybdenum peaks. You can see the light green paired with sort of a narrow peak width, the dark green with really wide peaks, and this blue set of paired peaks. So these are 3 different binding environments, but you'll notice that they're all the same distance apart between the 3 halves and the 5 halves peaks, and the full width half max for the paired peaks are similar to one another, even though different binding environments might have different peak widths or peak shapes. All right, so something to keep in mind, usually people are using XPS to understand a series of samples. So maybe an untreated sample versus a treated one, or things that vary in concentration versus just having a singular sample and you just need to characterize it by XPS. That's maybe not the best use of XPS. It's better to have sort of a specific research question you're trying to answer. So let's say you have 3 different samples that all have all 3 of these binding environments, just in different amounts. You should see that, these blue peaks are shifted in energy about the same away from the light green for all 3 samples. It wouldn't make much chemical sense for this blue to be the same binding environment in 2 different samples when one it shows up here and in another sample it shows up at a wildly different position in terms of energy. You'd also expect that the full width half max would be roughly the same from sample to sample. Basically, what would be changing is just the area under those peaks as the composition of those binding environments change. So that's something to keep in mind when you're analyzing your own data, but also looking at the research of what's reported out there. Okay. Another kind of good practice for analyzing complex samples like this is to run your own reference samples if you can. So if you have a complex mixture in your sample, but you have your starting materials, you expect those to kind of show up the same in your end material, it's just being mixed, then run those starting materials and try to see what the high resolution spectra look like. It can help you with fitting the complex mixture in the end. Another thing to keep in mind is, let's say you've assigned these binding environments to like molybdenum oxide, and molybdenum sulfide. I'm just making that up. What you should then see if you've assigned, a neighbor as being oxygen and sulfur for molybdenum, that in the same sample, you would be able to see oxygen and sulfur peaks. If you didn't see those, it wouldn't make sense to assign a binding environment of molybdenum bound to sulfur when you don't see sulfur on the surface. Okay, and then lastly, if you're doing quantification from one high resolution peak, one element, the area under these different binding environments corresponds directly to atomic concentration because it's just one element. But as soon as you start comparing different elements to one another, then the area does not correspond, and you have to use what's called the relative sensitivity factor to get to atomic percentage. So that's what kind of talking about here. Anecdotally, you can just see from this survey spectrum, the area under these peaks and the atomic concentration are not directly proportional. Fluorine has this biggest peak, but it's not the major component from the calculation. So to go from area to atomic percent, there's a calibration factor called the relative sensitivity factor. These are provided from the company for the instrument in how it's and is specific to how the instrument is set up. So kind of on a basic understanding, these calibration factors both depend on how the X-ray interacts with that electron orbital. So like how likely is that electron to be ejected? How does the electron travel through the material? How likely is it to be scattered? And then what the angle between the incoming X-rays and the path to the detector is, as well as a few other aspects. So we have a document from PHI that has these calibration factors for our instrument and for how it's set up. And those should be used for quantification, compositional calculations. And we have a library file that you can update in CASA XPS, which is the software that we have a license for that's not specific to our instrument. So those numbers need to be updated in CASA before you do any calculations. Okay. Keep in mind quantification accuracy can be rather poor for XPS. Did you have a question or no? Okay, never mind. Sorry. Yeah, so trying to see general trends from sample to sample is a good practice. Okay. Another common practice that might be used for XPS analysis is to reference your spectra to a specific energy. So typically samples are exposed to air and have some sort of carbonaceous material on the surface. So when you scan other elements for high resolution, you also scan carbon. And then if you can pick out where the carbon-carbon/carbon-hydrogen binding environment is within that carbon spectra, you set that peak to some value right around 285 EV, shift all of the data with it for that one measurement, and then you can compare one measurement to another. You can also then more easily compare your data to other data in the literature. You should always just report exactly what you did in your methods. Typically, spectra are shifting a little bit left and right each time you measure something from differences in sample charging. We're kicking electrons out of the surface of our sample, and so we might build up a slight positive charge. We do have what's called an electron neutralizer, where we can flood the surface with low energy electrons to try to mitigate that. Yeah. All right. Some other techniques that can be done in the XPS, I'll kind of go over briefly, mostly around depth profiling. So for trying to understand how samples might change within the top 5 to 10 nanometers of the surface, you can do what's called angle resolved XPS. However, this relies on your sample being extremely flat, and like the surface roughness needs to be negligible relative to the thickness of those layers that you're trying to analyze. Because as you can see here, if the sample surface face is, or I guess the path of the electrons coming out of the sample to the detector is normal to the sample face, then you get the deepest information, roughly 10 nanometers, let's say. If the sample is tilted relative to that direction to the detector, then you get a shallower depth of information. And so this shows you sort of a silicon wafer with silicon oxide on the surface at normal versus at an angle. And at the angle, you see this higher contribution of the silicon binding environment bound to oxygen rather than just silicon-silicon bonds, which you still do see. Okay. For depth profiling beyond that, people do what's called sputter depth profiling. So we have on our instrument a monoatomic argon ion gun. We can bombard the surface with these positive argon ions and basically blow away layers on the surface. These argon atoms are destructive, so we can only sputter inorganic materials. And even then, there's risk of layer mixing, damage to the sample, changing the chemistry of your sample. So you kind of have to keep that in mind when you're sputtering, measuring, and coming up with a sputter depth profile. As you collect those series of data sets, you might see changes in the binding environments as you go deeper, or composition, different elements coming in or out. And so typically people, after analyzing each of those data sets at different sputter points, then might put together one of these plots where the elemental concentrations change with sputter time. If you see this, but with sputter depth, that relies on having a standard for your sputter rate. So different materials sputter at different rates. Maybe there's sort of like a rule of thumb, this much per minute is sputtered, but because it can change based on the material, it's best to have your material in a known thickness and sputter that and get sort of a calibration constant for the sputter rate. I've put these other two ions up here, so a buckyball C60 ion, and then this gas cluster ion, because these are some newer technologies in XPS for sputtering. The larger atom cluster is used for sputtering organic materials, solely organic. It's not strong enough to sputter inorganic materials. And then the C60 is used for mixed systems. Yeah. I wanted to highlight two examples of XPS from our instrument published. So this is from the Finke group, where they were examining iridium nanoparticles they had synthesized, questioning the oxidation state, or rather trying to confirm that their particles were iridium 0. So handling them in a glove box, transferring them to the XPS with an air-free holder, they just observed this one iridium binding environment. And then after leaving the particles out in ambient conditions at room temperature and measuring once more, they started to see the growth in of this iridium oxide binding environment as well. This is an example from the Popa and Kipper groups, where they were creating these multi-layer coatings, the typo there, sorry, and nitrogen and sulfur peaks were indicative of their the treatment that they had done, so they were looking for confirmation to see those in the survey spectra. They also used the high-resolution spectra to assess some of the sort of compositional effects of their treatments. Yeah, and then lastly, I wanted to go over a few bits of what our efforts are to get a new XPS here at CSU. So we have twice submitted to the NSF MRI, and we're still waiting for feedback on, or just the news on the current submission round. We're targeting a Phi Genesis, so this instrument pictured here. It's the same company, but 30 years newer. So our current XPS was first released in 92. The Genesis just was released in 2 years ago. One big change for this new XPS would be spatial resolution. For the new XPS, you'd be able to use an X-ray source spot size down to just 5 microns, whereas on our current one, we don't get enough signal if we limit the aperture, and basically everybody is using a spot size of around 1 millimeter by 800 microns, or the next smallest one, which is 800 by 800 micron area. The new XPS would have this additional hard X-ray source, a chromium K-alpha source, so you can see much higher energy than the 1486 EV of our aluminum one. So this would allow you to have sort of two data points where you can measure those top 5 to 10 nanometers like we do now, versus with the chromium source, you get information to about 30 nanometers deep. Yeah, it also extends the energy range so you could see more photoelectron peaks. So visually assessing where you are on the instrument is pretty difficult on our current XPS, but in the new one, they have what's called scanning X-ray induced secondary electron imaging. So think of it as like a really crappy SEM image, because you are getting these secondary electrons kicked out, but your probe is not as fine as an electron beam in the SEM. But you do get kind of SEM-like images at low resolution, and that helps for choosing positions on your sample to analyze and sort of map areas. All right, just kind of logistically, things are a lot more automated for pump down, sample transfer. It would come with its air-free sample transfer holder for going from a glove box to into the instrument. And then in terms of neutralization, we would target the cluster argon ion gun, so where you could do both monatomic and cluster argon sputtering for either organic or for either inorganic or organic materials. And then the new system would also have UPS, ultraviolet photoelectron spectroscopy, kind of in a fully automated system, which is something that our current XPS is not operating. And that is a technique where instead of X-rays, you're using UV light to get at the valence structure of samples. All right, so that was a lot of words. Sorry for that. Here are some pictures. This shows you some example data of this is like that secondary, or the scanning X-ray induced secondary electron image, where you see sort of a quasi SEM image. They chose 3 different locations, did the survey spectra, found different compositions there, and then studying the silicon high resolution peak and assessing each of the spectra from these different points, they could color code this map to show which binding environments show up where in the sample. And the scale bar here is 50 microns. You can see this is at a much higher spatial resolution than what's possible for our current XPS. With the hard X-ray source, the chromium source, this shows you a quick example of having an aluminum X-ray source versus a chromium X-ray source. You can see some of the silicon metal below the oxide layer non-destructively. Get a sense of what's more on the surface of your sample, what's a little further down without destroying anything. And then this shows you on the right how, our aluminum K-alpha X-ray range is limited to up to basically 1400 EV, whereas with chromium, it's a much higher source, so you see all of these other photoelectron lines. Auger peaks are shifted again, like we talked about. But yeah. And then lastly, here's an example of some sputtering of organic PV materials, I believe. And these are just 2 different conditions for that sample. But yeah, this required using these gas cluster ion beams because the monoatomic argon ions would have completely destroyed the chemistry of what they were trying to analyze. Okay. This is more so for you all afterwards, but there's a lot of good resources out there on XPS. There's actually a lot of XPS being published these days, and not all examples in the literature are good, unfortunately. So much so that in 2020 and 2021, there were 2 full issues of papers published that are solely tutorials and guides with general information about best practices from sample preparation to referencing to analyzing your data, collecting data, etc. So I've linked both of those issues there. I'd highly recommend taking a look through them. There are really good webinars from the company that makes the XPS we have, Physical Electronics. So they have a YouTube channel. The handbook, as I've mentioned, we have access, or all of our users have access to. And then Cost XPS is the software that we have a license for. Analyzing the data, it's really powerful. It's not always the easiest to learn, but they have their own YouTube channel as well with tutorials. And then lastly, Thermo Fisher has a nice website where they just have a periodic table. You can click on an element and it takes you to a page of sort of short bullet points of what overlapping peaks that element might have with other ones, or kind of consideration, first steps considerations for doing an XPS when you have that element in your sample. Lastly, we have two elements leaving the arc, or two instruments that fall under surface analysis. So the contact angle goniometer and the ellipsometer. They just are not used enough to be part of the shared resource facility, and they may move into specific departments or research labs. But yeah, happy to answer any questions now. Thanks so much.
Any questions for Rebecca? You can also put them in the chat if you'd like to. Thanks, Rebecca. It was a great seminar.
Thanks.
I might have a question about the new XPS. Would it still have a sputtering option on it? Maybe I missed that.
Yeah, so maybe I glossed over that, but yeah, it would have what we have now combined with the gas cluster source. So just argon, no buckyballs, but you could do either monoatomic argon ion sputtering for inorganic materials, or you could choose the gas cluster option and sputter organic materials.
Notice someone is typing a question. And when will the new XPS be available?
Well, so we don't have any actual plans to have one. We're trying to get the money for it. So the NSF MRI is a grant that you can apply to, and we applied to it for the first time, didn't receive the funding. We applied to it a second time, and we just haven't heard back yet of whether we are going to receive the funding for the new instrument. So there's a chance they say no, and we're trying a third time. So currently there are no active plans for a new XPS to be here, but if the grant gets funded, then that's what we would target. And hopefully all of the functionality that we've outlined would still be in the budget and everything like that. So,
but people will get a new SEM on June
17th. It's true.
Yeah.
Yeah, I just wanted to highlight that, what we're trying to upgrade, because the current system is quite old. So, and what is possible with newer systems these days. So.
Other questions? Rebecca, you mentioned AFM. Is there an AFM on campus that people can use in case they want to do better resolution profiling?
Yeah, there is one. Let's see, I forget the name of the contact person, but there's a website that has the name of it and the person to contact, and you can be trained to use it as far as I know. I haven't spoken with them directly, but I've directed people that way. Yeah. Thanks. Here we go. I'll just put the link in here. So, yeah, the link to the AFM page is in the meeting chat. Sweet.
Someone else is typing. Mhm.
Nice.
Okay, well,
Cool.
if there's no questions, I will give everybody 10 minutes.